Hello and welcome to this video from the Waste Tutor. This is the first video of the Combinatorics unit, which is essentially a fancy name for saying counting techniques, that is, ways of allowing us to count things in more efficient ways. And what permutations deals with is ordered arrangements, that is, counting how many different ways we can order a bunch of different objects, for example. So in terms of the unit outline, the first thing we want to do is be able to solve problems involving permutations, and to do that the first thing I want to introduce you to is the multiplication and addition principle. So that's the first thing I'm going to go over, and after that I'm going to go over sort of the notation that you use, factorial notation, and NPR, and I will then also go over slightly more complex permutations questions, which involve restrictions with or without repeated objects. Another thing is that this can be paired with another branch of combinatorics known as combinations, and you can combine both combinations and permutations in certain questions where the problem demands it. So they can get relatively tricky, but if you're able to think about it logically, that's really the key to being able to solve a lot of these problems. Okay, so the first thing I'm going to go over are the multiplication and the addition principles. Okay. Essentially, what the multiplication and addition principles come down to is whether you can do something at the same time or you can't do something at the same time. And this is like a key fundamental aspect of permutations and counting techniques. The multiplication principle applies when you can do things at the same time, or kind of pair different ways of doing things with one another. To give an example, let's say you have 3 different pairs of shirts. So this is your first shirt, you've got your second shirt, and then you've got your third shirt here. Hang on. Okay, let's say you have these shirts, and then you have 2 sets of pants. So there's your first set of pants, and then your second set of pants, like this. Okay, and generally, in this case, the number of outfits that you can make from these is equal to 3 times 2, because for every one of these shirts, you have 2 sets of pants, and so you have 1, 2, 3 times 2. And this is referred to as the multiplication principle. So you can do these things at the same time. You can put a shirt on at the same time, and you can put pants on at the same time. Now, if we were to think about, let's say you are in Perth, and you want to go to Sydney, okay? And to do that, your options are you can take 3 planes, or you can take 2 boats. Okay, now you can't take a plane and a boat at the same time, but if you take the plane, you can't take the boat, and if you take a plane, you can't take any of the other planes. So in this case, you have 3 plus 2 different options, which is equal to 5, to get from Perth to Sydney. Okay, and so in this case, the addition principle applies because you can't do things at the same time. All right. Same time. All right, so that is the multiplication and addition principle out of the way. Now, the next thing I want to introduce to you is permutation notation, and how the multiplication principle and the addition principles kind of play into this sort of question here. So let's say I have 4 different objects. I have a square, I have a star, I have a circle, and I have a triangle. All right, and I want to figure out how many different ways can I arrange these 4 objects. Okay, now if I was to consider 4 different places to arrange each of these objects, in this first place, I would be able to put 4 of the 4 objects. Okay, now in the second place of these 4 places, now that I've used up 1 here, I only have 3 other objects to choose from. And so I can put 3 objects here. In the next place, I have 2 objects I can choose from. And the next one, I have 1 object I can choose from. Now, 4 times 3 times 2 times 1 represents the number of different ordered arrangements. Number of ordered arrangements, or permutations of those 4 objects. Okay? So it represents the number of ways I can arrange the square, the star, and the circle and the triangle into in a row, essentially. So for each time I have the square at the front, in the next thing I can have one of these, and the next one I can have one of these, and then the last one I can have one of these. Okay? Not specifically in that order, but I have like a bunch of different options that I can go through. If I choose the square, then I can either choose the star, the circle, or the triangle. Once I choose the star, I can either choose the circle or the triangle. Here I can choose the star or the triangle. Here I can choose the star or the circle, and so on and so forth, and that goes on and on and on. But essentially, a much faster way of representing this whole thing and counting out all the possible options is to simply use this sort of permutations formula. And if you notice here, what it's going is it's essentially a multiplication of a bunch of numbers that are decreasing down to 1. So what's happening is I've got 4 times 3 times 2 times 1. And this is a very common pattern that happens. If, let's say, I have a square, a star, a circle, a triangle, and a pentagon, then the number of ordered arrangements I can have would be 5 in the first spot, 4 in the next, 3 in the next, 2, and then 1. So 5 times 4 times 3 times 2 times 1. And now what 4 times 3 times 2 times 1 can also equally be written as is 4 factorial. And so this exclamation mark implies that if I have 4 factorial, that's equal to 4 times 3 times 2 times 1. The multiplication of 4 times consecutively decreasing numbers. This is equal to 5 factorial by that logic. So, factorial notation therefore refers to n factorial would therefore be equal to n times n take 1 times n take 2, so on and so forth until we get to 2 times 1. Now, an important property of factorial notation, in this case here, is that n factorial, for example, is going to be equal to n times n minus 1 factorial. And this is known as the recursive rule, or the recursive definition of factorials. It's particularly useful if, for example, we are trying to simplify something like 50 factorial over 49 factorial. In this case, we can write 50 factorial as 50 times 49 factorial, divided by 49 factorial, cancel them out, and we just get 50. Alright? So that's the recursive definition of permutations. Now, this is particularly important because there may be cases where we want to choose from a certain number of objects, but we don't want to arrange all of them. Let's say we have our square, circle, square, star, circle, triangle, and pentagon. And of these 5, we only want to select 3 of them. And so we have 3 places we can fill up. And in this first place, we can have 5 of them. In the next space, we can have 4. And then the next place, we can have 3. And that's equal to 5 times 4 times 3. Okay? So that looks kind of like 5 factorial divided by 2 factorial in this case. Now, this case involves selecting from n objects. Alright? And we are selecting, we have 3 places that we want to fill in. And I'm going to label the number of objects I have to choose from and the number of places I have as n and r respectively. So if this is how I'm labeling them, then generally a permutation can actually be written as n permuted with r places. And what that is equal to is n factorial over n take r factorial. That is the number of objects I have minus the number of places. In this case here, my number of objects is 5. So my n is equal to 5. My r in this case is 1, 2, 3. So in this case, this is 5 minus 3 factorial. And if we simplify that, we can see that's equal to 5 factorial over 2 factorial, just as we previously expected. Alright? So this is a very basic sort of permutation question. It involves, this is the case where the number of places we have is equal to the number of objects we have, but we can make that a little bit more difficult if we consider having a different number of places to the number of objects that we have. Now, we can't actually obviously have the number of places be more than the number of objects we have because that would be impossible. If we want to fill up 6 places but we only have 5 objects, that obviously is impossible. So don't consider that scenario. Okay? Now, we might have some slightly more difficult permutations questions. That is, we might have permutations where we have a couple of restrictions placed on it. Let's say we have 10 numbers, 0, 1, 2, 3, all the way up to 9. So this is 10 numbers. And we want to form an even number that is 4 digits long. Okay, so we have 4 places here. And this, for the purposes of this question, we can assume that 0 can obtain the first spot. And so, for example, examples like 0, 1, 2, 3, that is an example of a valid case. Even though in this case it wouldn't be even, but in this case. So this would be considered a correct answer, just for the purposes of this question. Now, so the key thing here is we have 4 places. Our n is equal to 10. Our r is equal to 4. However, we have this restriction here. N, it must be an even number. When we have permutations with restrictions, we always deal with the restrictions first. Deal with the restriction first. In this case, we have to have an even number. In order for this to be an even number, our last spot must be an even number. Out of 0 to 9, our even numbers include 0, 2, 4, 6, and 8. As a result, we have 5 options to choose from. Then we can consider the rest of the places. Now that we've used up an even number, we have 9 numbers left. Okay? And so we can fill this first spot up with 9, the next spot with 8, and the next spot with 7 as we use up the numbers. And so as a result, the total number of permutations we have here with the restriction is equal to 9 times 8 times 7 times 5. Okay? Now, we might additionally, this specifically here considers a case where we can't repeat the numbers as well. Okay, so this assumes that all of the numbers are different. However, we can have repetition of numbers, and usually when we're forming numbers, we do have repetition of numbers. Let's say we want an even number with 4 digits long, and we can repeat the numbers that we use. All right, in this case, we have 5 that can go in the last spot, and because we can repeat now, we can have 10 objects here, 10 objects here, and 10 objects here. Okay, that's because this here assumes that we don't, if we use one number, we can't use it again. This assumes we can repeat numbers. And so as a result, this is equal to 10 to the 3 times 5. This is with repetition. Okay, this here assumes all the numbers are different to one another. All right. We might also have cases where we are selecting from a group of people, they're trying to sit on a bench, and let's say some of them really, really want to sit next to each other. Let's say we have Adam, we have Brady, we have Christine, and we have Daniel. I'm just going to represent them as A, B, C, D. Let's say Christine and Daniel really want to sit next to each other on a bench. Okay, so this is my bench here, and I want to organize A, B, C, D, but C and D have to be sat together. It doesn't matter if C and D are in this order or in this order, but they want to sit next to each other. If we have grouping, this is referred to as grouping, we always consider the group first. And we can consider the group as one object. So we have 1, 2, 3 objects. And as a result, we have 3 factorial ways of arranging those 3 objects. Now within C and D, we can arrange C and D 2 factorial ways because we have CD and DC. So we have 3 factorial times 2 factorial, which is equal to 12 different possible arrangements. Now let's say Christine and Daniel definitely don't want to sit next to each other. In this case, we can kind of consider it as an exclusion. The total number of ways A, B, C, and D can arrange themselves on that bench is equal to 4 factorial ways. Now the ways where Christine and Daniel are sitting next to each other, as we know, is 3 factorial times 2 factorial ways. To consider the cases where Christine and Daniel are not sitting together, we subtract the cases where they are sitting together away from the total number of cases we possibly can have. So it's 4 factorial minus 3 factorial times 2 factorial, which is equal to 24 minus 12, which is equal to 12 possible ways, 12 cases. All right. So whenever we have two people that really don't want to sit next to each other, always consider the total number of arrangements possible and subtract the cases where they are sitting together. All right. So in this case, we've solved some problems involving restrictions with or without repeated objects. This involves without repeated objects. So in this case here, we've shown the number of 4-digit numbers that are even where the digits can't repeat. This shows the number of 4-digit numbers that are even where the numbers can repeat. This represents permutations with grouping. This indicates where two people are sat next to each other. This indicates where two people cannot be sat next to each other. We can also have A, B, C, and D really wanting to sit next to each other. And in this case, we have B, C, D. We can consider B, C, D as one group. And in this case, we have two objects, 2 factorial ways of arranging those. And within this group, we have 3 factorial ways that they can arrange each other. So let's say B, C, D all really want to sit next to each other in a row. Then that is how we calculate that. So anytime we have permutations with restrictions or grouping is another example of a restriction, all we do is we consider those cases, those restrictions or groupings first before we do anything else. That is the key to permutation questions with restrictions. That's all for this video. I will see you in the next one as well, which I'll hopefully upload soon as well. This is a very logic-based unit in spec. It's not just about being able to use the formulas, as you can see. I introduced that factorial notation, but realistically, it's more being able to consider how do we account for restrictions and how do we represent that mathematically. I'll see you in the next one. Bye-bye.